Hello, CSEC students. It's time for some chemistry. I am Andrea Knight Blackwood, and I'll be your teacher for this lesson. Let's get into it. So, last time we looked at the mole concept. So, at the end of this lesson, you should be able to convert between moles, mass, number of particles, molar volume of gas at STP and RTP, and also you should be able to define the term empirical and molecular formula. All right, so last time we looked at Avogadros number, 6.02 times 10 to the 23rd. What this is saying is that this is the amount of particles that is present in 1 mole of atoms, or 1 mole of molecules, or 1 mole of ions. How do we calculate number of moles? So we calculate number of moles given the number of particles and dividing that by Avogadros number. Remember, Avogadros number is 6.02 times 10 to the 23rd power. And we can represent this by using Na. Okay, so let's do just one question. A. So it's saying how many molecules of ethane are present in 1.5 grams of ethane. So this is where you're going to need your calculator, and I'm going to the board. The first thing we do is to write what we know. We know that 1 mole of a molecule contains Avogadros number. And what is Avogadros number? 6.02 times 10 to the 23rd molecules. Right? So this is what we know. So we always write what we know. We start with what we know. Okay? So the question gives us 1.5 grams of ethane. 1.5 grams of ethane. So 1.5 grams ethane. C2H6. So we are going to find the molar mass for ethane. Carbon we know has a mass number of 12, and there is 2 carbon atoms, so we multiply by 2, plus hydrogen, which has a mass of 1, and there are 6, so we multiply that by 6. So 2 times 12, 24, plus 6 is equal to 30. Remember, the unit is gram per mole. We have to always remember our unit. So it's 30 grams per mole. So how does this relate to the question? Now, 30 grams of ethane would contain 6.02 times 10 to the 23rd molecules. That's what Avogadros is saying. The question gave us 1.5 grams. So 1.5 grams of ethane would contain X, right? So what we do now, we cross multiply. So this is where math comes in. So 1.5 times 6.02 times 10 to the 23rd power divided by 30 would be equal to X. So let's put that in our calculators to see what we would get. So 1.5 times 6.02 to 23rd power divided by 30, and I got 3.01 times 10 to the 22 molecules. Hope you got the same answer. Okay, so B, you can practice on your own. All right, so let's move on to the law, Avogadros Law. So 1 mole of any gas, Avogadro is saying 1 mole of any gas that contains 6.02 times 10 to the 23rd would have the same volume under the same temperature and pressure. What does all of that mean? What am I talking about? All right, so there are 2 types. We have standard temperature and pressure, and we have room temperature. So let's look at STP. STP means standard temperature and pressure. Now, standard temperature and pressure is 22.4 dm cubed. The temperature, we use degrees Celsius, so it would be 0 degrees Celsius. In kelvins, it would be 273 Kelvin. with 1 atmospheric pressure, while RTP is room temperature and pressure. Room temperature is, of course, 25 degrees Celsius with 1 atmospheric pressure. But most importantly, the volume occupied is 24 dm cube. So remember, STP is 22.4 dm cube, while RTP is 24 dm cube. All right? So let's look how to calculate number of mole using all of this. So number of mole is equal to the volume of gas divided by the molar volume of the gas. All right? And a little pointer down here to remind you that STP is 22.4 dm cube, while RTP is 24 dm cube. All right. So let's look how we can apply this to our question. All right. Okay, so a sample of carbon dioxide has a volume of 56 cm cube at standard temperature and pressure. Do you remember what STP stands for? How much volume is occupied at STP? It is 22.4 dm cube. Okay, so the number of moles of gas that would occupy 24 at 22.4 dm cube. So first thing we do is to write what we know. What we know is that 1 mole of any gas at STP occupies 22.4 dm cube. Right? So 1 mole of any gas at STP occupies 22.4 dm cube. So how much does 56 cm cube occupies? So I'm going to write, because the question gave me 56 cm cube, so I'm going to write it here. The first thing we notice when we're going to work this question is that we know this, and this is in dm cube. The question gave us cm cube. So our units, they have to be aligned for us to work the questions. So we have to convert dm cube to cm cube. So the question gave us cm cube, so we have to stay in cm cube. Okay? All right. See if we can get this to come off. Okay. All right. So how do we convert from cm cube to dm cube? We have to multiply by 1,000. So we're going from the smaller unit to the bigger unit. So we're going to rewrite this. So 1 mole of carbon dioxide would occupy 22,400 cm cube. So the question wants how many moles? So X mole of carbon dioxide would occupy 56 cm cube. So there you're seeing that we have both units on the same side. So what we would do to get X now, we would cross multiply. So X will be equal to 56 divided by 22,400. Let me put that in my calculator. You should have your calculator. You should be working with your calculator, familiarizing yourself with your calculator. So 56 divided by 22,400. And my answer is equal to 0.0025 mole. Okay? And that's the number of mole. Notice that this is a small unit in comparison to this one, so we'd expect a very small number of moles. All right? So 1 mole of carbon dioxide would occupy 22,400. But I only have 56, so I would expect a tiny number of moles. All right, so the next question is saying, calculate the number of molecules. All right, remember that 1 mole of the molecule will occupy what? Avogadros number. So what is Avogadros number again? it is 6.02 times 10 to the 23rd power molecules, right? So if 1 mole would occupy Avogadro's number, I have this. This is what I was given in the calculations, all right? So if I'm just going to write that 1 mole of the molecule, which is carbon dioxide, occupies 6.02 times 10 to the 23rd. 1 mole of the molecule contains this number of molecules. Therefore, 0.0025 mole of carbon dioxide contains X, because we're calculating molecules. The question is asking us for molecules. All right, so we cross multiply. Multiply 0.025 times Avogadro's number will give us X. So it's 0.025 times 6.02 times 10 to the 23rd. All right, we can't be afraid of our calculators, right? So let's put this in our calculators. You must have a functional calculator, and you must familiarize yourself with your calculator. All right, so 0.0025 times 6.02 raised to the power of 23. My answer is 1.5 times 10 to the 21 molecules. All right, there we go. So you can try number 3 by yourself for your homework to see if you have understood how to calculate molar volume. Okay? All right. Let's look at one at RTP. So this question says gas X occupies 345.1 cm cube at STP. What is STP again? 22.4 dm cube. So you have to keep the number in your heads. So STP is 22.4 dm cube. That's the volume of 1 mole of gas at STP. All right, so gas X occupies 345.1 cm cube at STP. Calculate the number of gas molecules in the sample of X. All right, let's write what we know again. Okay, all right. Okay, so what do we know? We know that 1 mole of the gas at STP has 22.4 dm cube. Right? So we are given 345.1 cm cube. So what we're going to do now is to convert dm cube to cm cube. So how do we do that? Remember, we multiply by 1,000. So, we're going to rewrite that in our units that we're given. 1 mole of gas X contains 22,400 cm cube. Therefore, what is it asking us for? The number of gas molecules. All right? So it's asking us for molecules. So then we can rewrite this to say 6.02 times 10 to the 23rd molecules of gas X would occupy the same volume. All right? Now we are given 345 cm cube, so we put it on this side. So X molecules of gas X is present in 345.1 cm cube. And of course, we cross multiply. Cross multiplying is easier, so we tend to do that. All right, so 345.1 divided by 6.02 times 10 to the 23rd times okay. So x 22,400 is on my x, so I'll be dividing by 22,400. So we have to ensure that we know how to cross multiply and that we are cross multiplying properly. So 345 will be multiplying by Avogadros number. Thank you, Ruth Ann, for that. Okay, let's put that in our calculators. Okay, so 345.1 multiply by Avogadros number divided by 22,400. X is equal to 9.27 times 10 to the 21. And it's asking us for molecules. All right? Let's continue. All right, so that's enough. That's enough practice on moles. So the other questions that I gave you, you can practice for your homework. All right, so let's continue to empirical and molecular formula. Now, the difference between empirical and molecular formula shows the actual number of atoms present in the molecule, while empirical formula, the one with the E, shows us the simplest whole number ratio. So again, molecular formula shows the actual number of atoms. It's highlighted red. The actual number of atoms, while empirical formula shows us the simplest whole number ratio. All right. So how do we calculate empirical formula? How do we calculate empirical formula? So N is equal to molar mass dividing by the mass of the empirical formula. That's how we calculate N. So we're going to apply this to questions to see how we do this. So here is a table. It's showing you empirical formula difference. It's showing you the difference between empirical formula and molecular formula. So here we have water, H2O. What is the simplest whole number ratio for this? Can it be divided any simpler? So here we have 2 hydrogens, we have 1 oxygen. Now the integer for this is 1, so it cannot go any smaller. Let's look at hydrogen peroxide. The formula, the molecular formula for hydrogen peroxide is H2O. This, if I divide this by 2, I would get HO. So this is the simplest whole number ratio, and so this is the empirical formula. Right? Let's do another one. We have benzene. There are 6 carbons in benzene and 6 H's in benzene. This can be divided by 6. So the simplest whole number ratio would be CH. So if I multiply CH by 6, it would give me benzene, C6H6. And let's look at the final one, ethene. The molecular formula for ethene is C2H4. And C2 can be divided by 2. I'd get 1. And 4 will be divided by 2. I get 2. So therefore, the integer would be 2. So the simplest, the empirical formula would be CH2. All right? So let's do a question. Before we do a question, let me highlight 2 things. Now, we can determine empirical formula by using the masses of compounds and also by using the percentage composition. All right? So let's look at this question. We have 18.3 grams of a sample of a hydrated compound. It contains 4 grams of calcium, 7.1 grams of chlorine, and 7.2 grams of water only. Calculate its empirical formula. What am I going to do? The first thing I'm going to do, I'm going to write what is given. So let's write what is given. So we have 4.0 grams of calcium, and we have 7.1 grams of chlorine, and we have 7.2 grams of water. So the 18.3 grams is just to tell you what the sample contains. So we don't put that part in the question. Everything should come up to 18.3 grams. So I have calcium here, I put chlorine here, and I put water here. So the hydrated sample, hydration, hydrate means to add water. So we have 4 grams of calcium. We write 4. So in the first column, empirical formula is very simple. It's a 4-step process. It's very simple. So first, we write the mass, the given mass, right in the first step. Okay? So the first given mass for calcium is 4. For chlorine, it's 7.1. And for water, it's 7.2. Yes, it's 7.2. Right? What is the next thing that we do? The next thing we do is to find the number of moles that are present in the given mass. So we write number of moles. And how do we calculate number of moles? The given mass divided by the molar mass. So the molar mass for calcium is 40. For chlorine, 35.5. For water, the molar mass for water is 18. Let's put that in our calculators to see what we would get. Okay, so 4 divided by 40. Is 0.1. So we know that is 0.1 mole. Chlorine, 7.1 divided by 35.5. That is 0.2. 7.2 divided by 18. That is 0.4. So the first 2 steps are familiar. So let's look at the third step. The third step is we divide by the lowest number of moles. So let's write a little notation here to divide by the lowest number of moles. All right? And of the 3, which one is the smallest? 0.1. So we would divide 0.1 by 0.1. And the answer would be equal to 1. 0.2 divided by 0.1. The answer would be equal to 2. And 0.4 divided by 0.1. The answer would be equal to 4. So what is the final step? The final step now is to write what we have. So we have calcium, 1, chlorine, 2, and 4 water. Right? We know that water is already a compound, so we can't write the 4 right there. So let's put this all together to see how it would look. So the final empirical formula would be calcium dot 4 hydride, 4 water. All right? So CaCl2, we know that we don't write 1 in chemistry, it is automatically implied, dot 4 water, because it's a hydrated compound. All right? So that was a good one. All right, so here we have the workings for you. In case you use more than 1, use more than 2 decimal places, you would have gotten that as your answer. All right? Let's try another one. So there are 2 ways to determine empirical formula. We can do it by mass, and also we can do it by percentage composition. So we just did mass earlier, so we're going to do percentage. So let's go back to the whiteboard. So it says a sample of hydrocarbon contains 85.7% carbon and 14.3% hydrogen by mass. Its molecular mass is 56. So here we are to calculate the empirical formula and the molecular formula of the compound. So now they're asking us to calculate the molecular formula, and we're only given the percentage. So let's see. Carbon, we're given carbon in the question, we're given hydrogen in the question. Just carbon and hydrogen. Beautiful. All right, so how much percent of carbon do we have? We have 85. Let's try a different marker to see if we can get it brighter. 85.7%, that's what we're given. And the other hydrogen is 14.3%. Now, if we get percent, we can automatically convert it to mass. So let's start with our lines. So, first part is the given mass. So 85.7, we can just automatically convert it to grams. So it's 85.7 grams. And 14.3%, we can automatically say it's 14.3 grams. And what is the next step? That's right, we calculate number of moles. And how do we calculate number of moles? We divide the mass, the given mass, by the molar mass. So it's 85.7 divided by 12 to get the number of moles. 14.3 divided by 1. Work it and tell me what you get. I hope we have the same answers. So the answer is 7.136 for carbon, and hydrogen is 14.158, because we're dividing by not just 1 but 1.01, which is the molar mass or the atomic mass for hydrogen. All right? So let's see what our compound is. Our compound, the empirical formula for the compound is CH2. So how do we get the molecular mass from this? How do we get the molecular, how can we calculate the molecular formula from CH2? We calculate the molar mass for this empirical formula. So 12 is the mass of chlorine plus 2 hydrogens, that's 14. So this is 14 grams per mole. So if I get 14 grams per mole, how can that help me to calculate the molecular formula? Remember, in the question, it told us that the molar mass for the molecule is 56. I have 14 for my empirical formula. So what is it that I do? How is it that I can calculate my molecular formula? So, okay, my question gave me 56. So we divide 56 by 14. Dividing 56 by 14, my answer is 4. That still does not tell me the molecular formula. What I have to do, I have to multiply CH2 by 4 to get the molecular formula. So CH2 times 4. The final answer is the molecular formula is 4 times 2 is 8. So 4 times 1 is 4. 4 times 2, 8. So my molecular formula is C4H8. All right, so let's continue. All right, and you can do this one for your homework. So take a picture and do it for your homework. I'll tell you where to send it, send the answers. So let's review balance equation, chemical equations, writing and balancing equations. All right, so remember that equations are basically writing a representation of a chemical reaction, right? For example, the combustion of methane. So when we combust methane, we basically have to write a chemical equation for it, for the whole reaction. So CH4 plus O2 give us carbon dioxide and water, right? So we have to represent it. All right, let's take you back a bit. All right, so here we have the periodic table. Remember that our elements are represented by symbols. Our elements, they can contain one letter, which is a capital letter, or two letters. So the first letter will be a capital letter, while the second letter, a common letter. All right, so we can have either one symbol for our elements, or two letters in the symbol for the element. All right, so here is a compound, H2SO4. What does the 2 tells us? The 2 tells us that we have 2 hydrogen in the compound. There is no 1 for sulfur, but it is implied. So we have 2 hydrogens, 1 sulfur, and 4 oxygen in the compound. All right, so here is the equation again, the combustion of methane. So there are 1 carbon, 4 hydrogens in this compound, 2 oxygens on this side of the compound, right? But there's a big whole number right here, 2. What does the 2 tells us? It tells us that we need 2 molecules of oxygen to react with 1 molecule of methane. All right, so we're going to break it down a bit. So here is a different example. We have sodium reacting with oxygen to form a new compound, sodium oxide, right? On this side, on the left side, we have the reactants. On the right side, we have the products, right? We separate our reactants by using a plus, and we separate the reactants from the products by using an arrow. All right, we don't use equal sign in our chemical equations. All right, so please do not write an equal sign. So our reactants on the left, products on the right, separated by an arrow. Right? Lovely. All right, so let me help you to balance your equation with the law of conservation of mass. The law of conservation of mass states that in a chemical reaction, the quantity or amount of each element does not change. What does that mean? It means that, let me write it on the board for you. Now it means we're going to use sodium reacting with oxygen to produce sodium oxide. So let me use this side of the board. All right, so let's write sodium reacting with oxygen to give us Na2O. Let me write this a little better so you can see it. All right, let me write it over here. Since over here is ready, Na plus O2 to give us Na2O. All right. Now, I need to balance this equation. The reactants must be equal to the products. So, on this side, I have only 1 Na. On this side, I have 2 NAs. On this side, I have 2 oxygens. On this side, I have 1. So how do I balance the equation? I use only whole numbers, and I put them in front of the element or the compound. All right? So here I have 1. This is 2. So I put a 2 here. So now I have 2 NAs. I have 2 NAs. But what about the oxygen? I only have 1 oxygen on that side. All right? So if I put a 2 here, this will be telling me now that I have 4 NAs and I have 2 oxygens. So my oxygens are now balanced, but my Na, they are not balanced. So what do? I only have 2 on this side. I can easily change this whole number from 2 to 4. So if I put a 4 there, now I have 4 NAs and I have 4 NAs on that side. I have 2 oxygens and I have 2 oxygens on that side. So my equation is balanced. And that's what the law of conservation of mass is telling you, that you must have the same amount on each side. All right? Let's try this one. Are these 2? So potassium reacts with hydrochloric acid to produce potassium chloride and hydrogen gas. So let's write that. Potassium reacts with hydrochloric acid to produce potassium chloride and hydrogen gas. Now, when you're writing your equations, you must include your state symbols. To include your state symbols, you would have to remember your solubility rules. All right? So let's include our state symbols in this equation. We know that potassium is a solid. All chlorides are soluble. And therefore, the question even tells us that hydrogen is a gas, so we just write G. So AQ for aqueous when it is soluble, and S for solid. All right? So let's look if this equation is balanced. I have 1 potassium here. How many do I have on this side? 1. I have 1 hydrogen here. How many do I have on this side? I have 2. So what is it that I need to do? I put a 2 in front of the hydrogen right here. So now I have 2 hydrogens and I have 2 on this side, right? So what about the chlorines? Now I have 2 chlorines. What do I need to do? I have 2 chlorines, so I will put 2 in front of the compound. So now I put 2 in front of the compound. Now I have 2 potassium and 2 chlorine. So because I now have 2 chlorines on this side and 2 chlorines on this side, the chlorines are balanced, the hydrogens are balanced. But the potassium is not balanced. What do? I just put a 2 right there and the equation is balanced. So now I have 2 potassium, 2 hydrogens, 2 chlorines. You have to remember that the 2 is multiplying by the 1 for the chlorine. So 2 chlorines on that side. And you can do the other one for your homework. So that's all for today. But if you have any questions, please send them to Television Jamaica Facebook page at Television Jamaica or Instagram at television_Jamaica, or use the hashtag TVJ Class Time, and make sure to join us again tomorrow for more CSEC and CAPE classes. Take care.
It's here. Interactive classes for all ages on the School Time channel on onespotmedia.com. With a combination of live Zoom classes and recorded class time, Schools Not Out lessons, and numerous educational content, we've created a comprehensive 24-hour channel dedicated exclusively to educating our nation's youth. Early childhood through to primary, secondary and tertiary, it's one stop on one spot for education 24 hours. Brought to you by the Ministry of Education, Youth and Information in association with Television Jamaica Limited.